We're going to take up a number of interesting algorithms that compute useful properties of entire streams without storing the entire stream or most of it. And here, unlike our previous discussions about streams, we're not just interested in querying a window of recent items, but of learning something about the entire stream. First, we'll look at Bloom filters. This trick enables us to select only those items in a stream that are on some list of items, even if the number of items on the list is so large that we cannot do a comparison of each stream element with each element of the list. Next, we'll look at random sampling of streams in a way that allows us to be consistent about which items we select, even if we see an item many times in the stream. And an interesting problem that comes up in many different applications is estimating the number of distinct items in the stream. The obvious approach, where we list all the items we've ever seen and compare each new item with each of them, can require too much time and space, even if we use an indexing scheme like a hash table to make the test efficient. If we're willing to forego an exact answer and be content with an estimate, we can do something much more space efficient. Finally, we'll talk about the idea of moments of a stream. The number of distinct items turns out to be a special case of zeroth moments, but we'll give a general definition when we arrive at that topic of moments. I want to explain why we need Bloom filters by using an example application, crawling the web. A web crawler uses many tasks, perhaps at different processors, to crawl pages. The crawler maintains a list of all the URLs it's already seen. Its goal is to explore the page at each of these URLs to find the additional URLs, the links on the page. Each URL on the list will be assigned to some task whose job is to look at that page and report back any links it finds. But we don't want to have the same URL get onto the list twice, because then we would waste time crawling its page twice. So every time a URL comes back to the central controller, it needs to determine whether it has seen that URL before and discard the second report if so. Now we could create an index, say a hash table, to make it efficient to look up a URL and see whether it's already among those we've seen. But the web is big, and this index would not fit in main memory. We could store it on disk, but having to do a disk access every time we got a report of a URL would be very, very time-consuming. It's possible to shard the index across several processing nodes, so each is responsible for only a small subset of the web and could therefore keep its portion in main memory. But there's a better way to get almost exact answers about whether a URL has been seen before while using much less time and space. When a URL arrives in the stream of reports from the crawling tasks, instead of looking it up on disk, we can pass it through a Bloom filter. This filter will say either that the URL has been seen before or not. If the filter says it has not been seen before, the URL will be added to the list of URLs that need to be crawled, and eventually it will be assigned to some crawling task. The bad news is that occasionally the Bloom filter will give a false positive. That is, it will say the URL has been seen before when in fact it is not. That would be bad if the URL were the gateway to a part of the web that could only be reached through that URL. However, if that is the case, the part of the web we cannot reach is not very important anyway. Any important part of the web has many links from many places. That's the PageRank idea. So missing one link will not affect much, if anything. The good news is that if the Bloom filter says the URL has never been seen, then that is true. That is, there are no false negatives. Okay, enough of a sales pitch. Let's look at how a Bloom filter actually works. The filter itself is a large array of bits, perhaps several times as many bits as there are possible elements in the stream. The bit array is manipulated through a collection of hash functions. The number of hash functions could be as little as one, although several is better. Even a few dozen hash functions could be a good choice in some situations. Each hash function takes a stream element and produces a value that is one of the positions in the array. It is important that the hash functions be independent. It should not be possible to predict the result of one hash function from the result of another. So we're going to start with all the bits of the array equal to 0. And now, suppose an element x arrives on the stream. We compute the values of h of x for each hash function h in our collection. That gives us some number of bits. Turn each of these bits to 1 if they were not already 1. So here's a tiny example of how a Bloom filter works. Okay. We're going to use an array of 11 bits. We'll assume the stream consists of integers, and we'll have two hash functions. The first, h1, is computed from an integer x as follows. We're going to write x in binary. For h1, we use only the odd positions, counting them from the right. That is, we get position 1 is the low order bit, position 3 is the 4th place, position 5 is the 16th place, and so on. Looking only at the odd position bits, we get another binary integer. Suppose that integer is I. Then compute I modulo 11, that is the remainder when I is divided by 11. That's the value of h1 of x. Okay. h2 of x is computed in exactly the same way, but from the even positions of the binary representation of x. So here's what happens when 3 integers arrive at the stream input. Initially, all 11 bits of the Bloom filter are 0. Okay. The first integer is 25. We show its value in binary with the odd-numbered positions counting from the right in black and the even positions in red. h1 is formed from the odd position, and we see 1, 0, 1. That's 5 in binary, and 5 modulo 11 is 5. So that's the value of h1. The even positions are 1, 0, and that's 2 in binary, and 2 modulo 11 is still 2. So that's the value of h2. So we therefore set positions 2 and 5 of the array to 1. You see the new values in blue. Note that we're counting positions from the left end and starting at 0. The next integer is 159, and you see it written in binary here as well. The odd positions in black form 0, 1, 1, 1, which is 7. And the even positions form 1, 0, 1, 1, which is 11 in decimal, and 11 modulo 11 is 0. So that's how we get the 7 and the 0 as the two hash values. You see positions 0 and 7 here in blue have been turned to 1. Third to arrive is 585. The odd positions form 0, 1, 0, 0, 1, and that's 9. 9 modulo 9 is 9 modulo 11 is 9. The even positions form 1, 0, 0, 1, 0, which is 18, and modulo 11, that's 7. So we set bit 7 and 9 to 1, but bit 7 was already 1, so we make no change. Bit 9 is set to 1, as you see here. We've seen how to set bits to 1 when we add elements to the set we're representing with the Bloom filter. Now we need to learn how to test an element for membership in the set. Let the element we want to test be y. Apply each of the hash functions associated with the Bloom filter to y. That gives you a set of positions. If all these positions are 1, then we say y was seen before. If y was seen before, then surely all of these positions would have been set to 1, so we will surely say yes. Unfortunately, there can be false positives, since it could be that we never saw y, but some other combination of elements managed to turn on all the bits that y would turn on. If one of the more of the bits is 0, then we'll say y was never seen. That's surely correct, since we know that each would have been set to 1 if y had been seen. That is, there are no false negatives. A point worth noting is that insert and lookup can involve a single set, as in our example of crawling the web, or there can be two distinct sets. If the elements that we look up become part of the set that the Bloom filter is to represent, then when doing the lookup, if we find some bits are 0, we set them to 1. However, we can also use a Bloom filter to compare two sets. We form the Bloom filter from one set, and then we test each element of the other set for membership by doing a lookup. In that case, the zeros we find are left as zeros. Let's take up an example of how we test membership in a set. We'll start where we left the previous example. We had inserted 3 elements, 25, 159, and 585, into the set, which left the Bloom filter looking like this. Suppose we now want to look up 118, which is this in binary. Now, the odd positions form 1, 1, 1, 0, which is 14 in decimal. Thus, H1 of 118 is 14 modulo 11, or 3. The even positions give us 1, 0, 1, which is 5 in decimal, and 5 modulo 11 is 5, so H2 of 118 is 5. To test membership of y in the set represented by the Bloom filter, we thus look at bits 3 and 5. Bit 3 is 0. That's actually this bit. Bit 5 is a 1. That means 118 could not be in the set because both would have been 1 if so. We say no, and that is the correct answer. I want to do a little ugly math to explain how the Bloom filter performs as a function of how big the array is, how many hash functions are used, and how many elements are inserted into the set that the filter represents. First, it should be evident that the false positive rate will be lower if there are fewer 1s in the array. When we hash an element not in the underlying set, the probability we find a 1 at that position is the fraction of 1s in the array. If we have k hash functions, then the probability that an element not in the set will be reported to be in the set is the fraction of 1s raised to the kth power. So what is the fraction of 1s? There surely cannot be more 1s than there are elements inserted times the number of hash functions. In practice, it will be almost as large as that, but collisions where two different hashings coincide and set the same bit to 1 will make the actual number slightly lower. At first, when almost all bits are 0, collisions are rare. But suppose 50% of the bits are now 1. If we apply one of the hash functions to a new element, there is a 50% chance that it will lead us to a bit that's already 1, and thus the number of 1s will not change when we apply this hash function to this element. I like to think of picking random bits of a Bloom filter to set to 1 as throwing darts at a collection of targets, one target for each bit of the array. So suppose we have d darts. In our intended application, d would be the product of the number of inserted items times the number of hash functions. Also, let there be t targets. T would be the number of bits in the array. What we want to know is how many targets are hit by at least one dart. These are the bits that get set to 1. To calculate this number, start with the observation that if we throw one dart, the probability that a given target is hit is 1 over t. And if we throw d darts, the probability that none hit the target, that is, the bit remains 0, is 1 minus t well, sorry, 1 minus 1 over t to the power d. That is, 1 minus 1 over t is the probability one dart does not hit. And when we raise this to the dth power, we get the probability that no dart hits. I'm going to rewrite the power d as t times d over t. Obviously, that's just another way of writing d. But the reason I want to do that is that this part, the 1 minus 1 over t, all raised to the tth power, has a well-known approximation as long as t is large. It is 1 over e, and e, the base of natural logarithms. 1 over e is about 0.37. In this case, t is certainly large since it is the number of bits in the array. And thus, a very good approximation to the fraction of zeros that remain is e to the minus d over t. I write it this way since 1 over e is the same as e to the minus 1. For example, let's use a Bloom filter consisting of 1 billion bits, and let's use 5 hash functions. Suppose we insert 100 million elements. And then we do half a billion hashes, so we might set to 1 as many as half the bits in the array. In terms of darts and targets, t is 1 billion targets and d is 500 million darts, or half of t. Using the formula we derived on the previous slide, the fraction of bits that remain 0 will be e to the minus d over t, or e to the minus 1/2. This value is 0.607. Or put another way, the fraction of ones will be 0.393, somewhat less than half. The fact that it is less than half is explained by the existence of collisions as we apply all the hash functions to all the elements that are inserted. From this information, we can calculate the probability of a false positive. For element y to be a false positive, all 5 hash functions must take it to bits that are 1. The probability of one hash function doing so is 0.393, and the probability that all 5 do is that raised to the 5th power, or 0.00937. That's a little less than 1%.